Weldability. The definition. It's the capacity of a metal to be welded under the fabrication conditions imposed into a specific suitability design structure and to perform satisfactorily in service. That's the American Welding Society. So basically boiled down in my world, that says how easy is this stuff to weld, and is it going to break after we get it stuck together? So how easy is it to weld? And we'll start out with the easy stuff, the carbon steels, and then we'll kind of work our way through to the upper ends of the carbon steels. But we're just going to take an overview of it. I'm not going to get out in the weeds talking too much about, things like ASME P15E, the 9 chrome materials that are just finicky as heck. I'm going to mention them, but I'm not going to. You could do a 3-hour PowerPoint presentation on how to weld the 15 or the P15E, or the 9 chrome 1 moly, I think it is, materials. So those we could go in there, but we're not going to. We're just going to give a overview, a flyover, see what happens. So when we're talking about welds, the two main mechanical properties that we're talking about are tensile strength and impact toughness. These are the two biggies, because you could have a material that is, got great impact strength and then it shatters like glass. Or you could have something that's got really good impact toughness and then it's really gummy and got no tensile strength. It just stretches and stretches and stretches. So, it's kind of finding that sweet spot for ferrous materials, particularly steels. You want that, the ability to absorb some energy, and you want the tensile strength, that fits the design criteria. So these are the two ones we're looking at. And generally, everybody is looking at the whole, all this stuff was started way before any of us were alive. And they realized, tensile strength and impact toughness were the two big criteria for welds and materials that are made out of steels and irons and just ferrous materials in general. Carbon equivalent. This is something that's going to come into play in regards to both preheat and post-weld heat treat. We keep talking about chemistry, and this is how we figure out our carbon equivalent. This little equation would be loss of words there for a second. Steels with a carbon equivalent below about 0.45 are readily weldable with appropriate procedures. So if you've got a material and you crunch your numbers and you look at your chemistry and it comes out below 0.45, you're probably not going to have problems with it. C's greater than 0.45 indicates a need for caution. Remember I said, talking about caution, this should throw up a caution flag. Well, this is it. If anything above a 0.45, that's when you need to start having preheat and whatnot. Worked for a company years ago, and we'd always get a call from their. It was always a situation where they wanted the welding engineer to come bail them out. They'd made a weld on one of the components that had been in the field. And then they're like, and we'd ask, well, what's the material? And they'd tell us, and we'd be like, okay, where's your weld procedure? How much preheat did you use? Well, we'd look at the material, me and this other engineer, and the carbon equivalent would be way higher than 0.45. And they had just welded this stuff cold, and then it would end up with a crack in it or something. And so a lot of times you need to look at this kind of stuff. And a lot of times, you deal with, service people or manufacturing engineers. They just want to get it out of the door, and they might not, they'll grab a welder and then tell the welder, oh, just weld this, just weld it up. And the welder doesn't know what it is. He's just following marching orders. So he gets some 7018 or some ER70S6 and welds on this piece and calls it good. And then, he's in trouble when it cracks later on. So Yeah, that's one of those things that just drives me nuts is when somebody says, well, can't you just weld it? Well, no, I don't know what it is. It's like giving somebody, a mechanic, a car and saying, just fix it. Throw some Volvo parts in that Chevy So anyways, long story short, carbon equivalent, very important concept. This whole presentation I've been preaching chemistry, haven't I? Talking thickness and chemistry in regards to preheat, weldability, post-weld heat treat. Those are the biggies. So, something to think about. Hardness testing and tensile strength. In carbon steels, there's a direct relationship between hardness and tensile strength. The harder the steel is, the higher the tensile strength. Here you can see on the x-axis we've got tensile strength, and on the y-axis we've got hardness, Brinell. And as you can see, as the hardness increases, the tensile strength increases. So generally, if you've got a soft, mushy carbon steel, the tensile strength isn't going to be very high. And on the flip side, if you've got something that's really hard, odds are it's got a very high tensile strength. Something to keep in mind while dealing with ferrous metals, specifically steels. So the factors affecting weldability are the steel composition and processing. What's in that material? You've got iron, you've got some carbon, and then what else have we thrown in there? And then, in addition to that, how has it been processed? Did we quench it, temper it, do some kind of heat treating to get it to the material strengths or the particular variables that we're looking for? We want to look at, the weld metal and the HAZ properties. When we weld this material, what happens? How's the weld metal going to come out? And then what happens to the heat affected zone on the base material? What happens in there? Choice of welding variables can, affect the weldability of steels. What's the weld process? Are we travel speeds? What kind of fluxes we're using? There's a bunch of different ways that a organization can get themselves in trouble in regards to welding steels. And pre and post weld processing affect it. Does this stuff need preheat? Does it need post weld heat treat? What do the codes say? What does the organization or the outfit that made the material, the manufacturer of that specific steel, what do they say to do with this stuff? How do they say to pre and post weld process the material? So these are all things that affect the weldability of steels. And when you're digging in and you're just trying to decide how you're going to weld a specific steel, these are things you need to look at. If not from a checklist point of view, just from a human nature, or I guess within your mind as a welding professional, you need to realize, okay, these are some things that could go bad on me, and I need to have my bases covered. I need to know what's going on here and have a plan to deal with these things. Warning signs. We'll throw this one right out there because anytime I look at a weld procedure, I look at the filler metal first. What are we welding? I look at the filler metal and the base metal, but generally filler metal first because I don't know every base metal, so I'll come back to that. I do come back and look at the base material, but the first thing I look at just as a cursory glance is what is my filler metal. And if it's got an 80 or a 90 in it, then the next thing I'm going to look at is, are we preheating, post-weld heat treating, thickness? What are we doing with this stuff? Because you got to, if it's got an 80 or a 90 in that tensile strength, an 80 KSI or a 90 KSI. And I just used shielded metal arc welding as an example. This could go for, any materials that, gas metal arc, gas tungsten arc, flux core, whatever. But if you look at it and you see it's an 80 or a 90 KSI material, be careful. Look for that train coming. Realize that there's going to be some extra work, and you're probably going to have to educate your welders too, if they aren't already educated. Your foreman, your quality control people, everybody needs to be on the same page as to what the expectations of how to weld this material and how it needs to be done. Because a lot of guys just don't understand. They've never, they've welded with 70-18, and then you throw them some 90-18, and they're like, oh, all right, we don't really need, preheat or post-weld heat treat or whatever. There's a lot of different ways things can go wrong, and they have gone wrong. So just something to keep in mind. One place where you're going to run into this is, the weldability of steels is in AWS D1.1. And AWS D1.1 breaks their steels, and I'm just talking about the pre-qualified materials. They've got everything broken out into 4 groups. Group 1 is the material that's pretty readily weldable, and you really are going to have to work to mess it up. And I'm not saying it can't be messed up, but it's generally a pretty forgiving group of materials. And that's why if you read through, their expectations for pre-qualified materials for group 1, it's a group of materials that you can weld with, cellulose materials like a 60-10 or whatever. And you look over here, I've got 3 columns here. I've got the groups, and then I've got the second column is materials, a material I pulled off their list. And then the third row over there, the ones that are just outlined, the E70 XXX, that's a material. That's a filler material. So you can see we can use anything there. We don't have to use low hydrogen. We can weld it with that stuff, and it's not an issue. So we could pick E7010, and we could weld with it, and there's no problems. Well, as we go down to group 2, and let's say we go with an ASTM A516, and I forget the grade that I had on that one. Well, on there, they've given us 3 options. You can go with a 70-15, 16, or 18. 70-18 is what I'm most familiar with. I think I've dealt with some 16 at one point, but E70-18, that's pretty much the garden variety, off the shelf. Everybody makes it. It's a pretty good welding rod for welding with low carbon, the structural grade steels. So you can weld with that stuff and not get into too much trouble. But there might be a situation with the thicker materials. You're going to need a little higher. You're going to need a little bit of preheat, and you're probably not going to need some post-weld heat treat. But it's giving you it's telling you in that group too, if you read through AWS D1.1, it's a little more testy. Those materials take a little bit more care. But for the most part, if you act like a professional in the welding industry and you follow the rules, you're probably not going to get in too much trouble with those materials. Well, by the time you get to group 3, you're dealing with something like an ASTM A572 grade 60. So in those, you have your base metals that come off, or your filler metals for those base metals that come off the chart in clause 3. All of this is in clause 3, which is like a chapter, but clause 3 for AWS D1.1. So in there, you've got the 80 KSI materials. Well, like I said before, anytime I see an 80 KSI for a filler material, I know we're dealing with something that is a little more delicate. I don't know if delicate's the word, but you have to handle it with a little more care. You need to make sure that your preheats and you're not cooling it too quickly when you're done welding on it, and that you're generally following the rules. The people that put together AWS D1.1 and this list of pre-qualified materials and how to weld them, they've been at this for decades. So they're pretty much the world experts on these materials and these filler materials for use with these base metals. So, but like I said, anytime you see an 80 in there, that's a red flag to me. Doesn't necessarily mean we're going to have problems, but it just means slow down, caution. Let's do our homework. Let's make sure that the welders are on board, that we've communicated everything to everybody, our expectations, what can happen, what I don't want to see happen, etc. Then we get to group 4, and there's only like 3 metals listed as being pre-qualified for group 4 in clause 3. ASTM A852 is one of them. You can use the 90 KSI materials with that. But once again, you're going to have a little higher preheats. You're going to have to, these are a little more temperamental than even the Group 2 materials. So, you got to tread with care when you're in this, when you're welding in this zone of the universe. So just something to keep in mind. But, when we're talking about weldability, that's what we're talking about. There's different levels, and this is one way it's broken out with, carbon steels. So just something to keep in mind as you tread forward. Okay, now we're going to switch over to ASME P numbers. I did another presentation where I got off in the weeds and just talked about ASME P numbers. ASME P numbers are the assignments have been based on comparable base metal characteristics such as composition, weldability, brazability, and mechanical properties. So the American Society of Mechanical Engineers years ago got together and put together base materials into groups, and they called them P numbers. So, and there it's based on how well does this weld, what's the composition, is it pretty close to me in this stuff, mechanical properties, all of that. So that's what they put into it. So my mind thinks in P numbers when I'm talking about metals. I've been at this going on 30 years. So, if somebody's talking to me about a metal, I got to look it up and think of it as a P number. It's that stuff. It's going to weld like that. It's going to weld like an austenitic stainless steel, or it's going to weld like a carbon steel. So, but we're going to do a little bit of a deep dive into ASME P numbers and how they react, and just some general post weld and preheat numbers. Go from there. Okay, so ASME P numbers. Here's a list of some of them. I'm going to cover some of these on a couple of slides, but you can take a look-see here at ASME, the American Society of Mechanical Engineers, has grouped these together. Group 1 is carbon steels. P number 2, it's not used, but I asked the guy that was on ASME Section 9, why is there no 2? He said 2 is wrought iron. This is just trivia. Like the stuff the Eiffel Tower in Paris is made out of is wrought iron. Back in the day, I guess they used to make pressure vessels out of it back in the 30s and 40s. Kind of interesting. Useless trivia for you. So then by the time we get to 3, 4, 5, 5A, 5C, you see we're throwing some chromium in there. That's generally for, you'll see this a lot in power plants, steam piping and whatnot. So that stuff's a little more difficult to weld as you start adding things like, chromium and molybdenum in there. Then we got ASME P number 6 is martensitic stainless steels. Those things I think can be a little onerous to weld because it's a martensitic material. Anytime you see the word martensitic in a description of anything, I see the word martensitic and I'm like, whoa, time out. I got to go read and see exactly what this stuff is. So if you see a 90 KSI in carbon steels or an 80 KSI and you see the word martensitic, those to me are warning flags. It's like, okay, I'm going to have to go read. Maybe there's nothing, but I'll spend a half hour seeing what I'm welding before I charge on to, anything with the word martensitic in it. Here we've got, ferritic stainless steels, austenitic stainless steels. Group or P10H, I've dealt with duplex and duplex stainless steels. Generally there you're trying not to put too much heat into the material because that'll just mess it up. So you want to keep your heat inputs on that material generally pretty low. Any weld procedure you qualify with that, you got to keep your interpass temperatures low. Used to work at an outfit where we did a weld procedure on like 12-inch thick duplex stainless steel, and we couldn't get the interpass temperature above a couple hundred degrees, so it would take us days to do the weld coupon. I'm not kidding. It was a thick material, and the welders would just sit in there until it cooled down again. All right, run another pass. The other one we want to look at here is 15E, which is 9 chromium, 1 molybdenum. These are getting to be more popular in steam power plants, and these are really, what are they, creep-resistant materials. Creep resistance enhanced ferritics, I think is what they are, CREFs. But these things are pretty onerous. You got to have the preheat right. You got to have the post-weld heat treat right. There's an intermediate post-weld heat treat that you've got to have in there and done correctly. So, if you see anything that's like 9 chromium, 1 molybdenum, that's a big warning flag. You're on thin ice there. You need to do some reading if you ever have to qualify a weld procedure with that type of material, because that stuff is, you're definitely swimming in the deep end of the pool, and not only are there sharks, but there's piranhas in that pool with you. So you got to know what you're doing if you're going to weld the 15Es. Not a very forgiving group of materials, but something to keep in mind. So because you've got ASME boil and pressure vessel code section 1, you've got B31.1, B31.3, a whole bunch of different welding codes. So I'm just going to take one of them. I'm going to go with ASME section 1. And we're going to, because more or less most of them are pretty similar. There's some nuances and caveats from one to the other where you can do something in one of the codes where you can't do it in another, or vice versa. But for the most part, they all address the material more or less the same. You just need to be careful and read whatever specific code you're working on, and don't go off a different code. So preheating from PW 38.1. The need for and the temperature of preheat are dependent upon a number of factors such as chemical analysis, degree of restraint of the parts being joined, elevated temperature mechanical properties, and material thicknesses. So here you're looking at chemical analysis. What's in that steel? How big is the restraint? How hot is this thing going to be when it's up and running? And, the material thickness. Material thickness makes a big difference. Are we welding in regards to preheat? Are we welding something that's the size of, sheet metal or half an inch thick? Or are we welding a material that's 7 inches thick? So preheat, these are some things you really got to look at. Chemical analysis and material thickness being the two biggies that I generally gravitate towards. Not that the others aren't important, but the way my mind works, I go chemical analysis and material thickness, and then I look at the other information, kind of get my mind wrapped around it first, and then charge into restraint, and then, what temperatures this stuff going to run at. I'm going to slam through some minimum temperatures for preheating. These are all from ASME boiler and pressure vessel code section 1. So P number 1, which is similar to the group 1 and group materials mechanically in the AWS D1.1. This is the low. You see the first thing they're throwing out there is the carbon content. The carbon content, if it's in excess of 0.3 and the thickness of the joint is in excess of an inch, you got to take it up to 175 degrees F before you start welding on it. But if it's less than an inch and it doesn't have a very high carbon content, you go to 50 degrees. It's pretty forgiving material. So this is, but once again, if your carbon content gets up there in excess of 0.3 and you got a really thick material, 2-3 inches, you got to heat it up to 175 degrees before you strike an arc on it. So P3 is a little more onerous than a P1 material. So here, you go to 175 for a material that has either a specified minimum thickness or tensile strength of 70 psi, or a thickness in excess of 5/8 of an inch. So for all other materials, you can go to 50 degrees. So if it's in excess of 70,000 PSI, you got to go to 175. Or if the thickness of the material is 5/8 of an inch or greater, you go to 175. For everything else, you just go to 50. So you can see as we're kind of going through this, we're getting a little more difficult to deal with. P4 materials, you've got, 250 for anything that's in excess of the tensile strength's in excess of 60,000, or the thickness of the joint is in excess of half an inch. So you can see as we're kind of ratcheting it up here, P3, P4, those materials all need a preheat. Group 6 or P6, that needs 400 degrees F before you even start. So that's telling you, that this stuff is pretty tricky to deal with. Here's some other materials. P7 and P8. P8 is your garden variety carbon or austenitic stainless steels. You don't preheat them. You'll mess those up if you preheat them too much. And then the P number 10A and these guys, they all get a little bit of preheat, and an inner pass. So I have never really dealt, I don't think, with 10A and 10I, but these are just some examples of, as you're going through the welding code, ASME boiler and pressure vessel, section 1. This tells you how difficult some of this stuff is to deal with and what you need to do. But they line it out for you for the most part, and with a little bit of research and putting together your documentation, you can get most of the stuff welded pretty readily. But once again, it gets back to weldability. Stuff that that needs a 300 degree F preheat is in a inner pass temperature of 350 to 400 is probably a little more onerous than just welding some carbon steel. Weld it and you're done with it. So here's a couple that I've dealt with in the past that were pretty difficult. The first one is like the group 5A, 5A, 5B. These things are kind of difficult to deal with. Not difficult, but you're preheating it to 400 degrees. So I don't know if you've ever welded or had to preheat something, but preheating something to 100 degrees takes a lot of thermal energy to get it there. To get something to 400 degrees, especially if it's a thick material, you are talking a lot of heat and a lot of fire. So it's just something to think about. And, they're throwing, they also throw in there in the 5A and 5B, you need to look at the materials and make, what's the chromium content, So there's some things you really need to look at. So for P15E, I worked for a company that used to do some P15E material. And this is 400 degrees F. Before and a tensile strength in excess of 60,000. Most of that stuff does. And then you have to look at the chromium content. If it's above 6 and a thickness of the joint in excess of half an inch, So you're either going to 400, and if you aren't going to 400, you're going to 300. So this stuff is very particular, and you can have all kinds of cracking related issues if you don't follow, the recommendations on how to weld this stuff to the letter of the law and follow all the rules and really take care of this stuff. But, we're not here to get into the weldability of P15E. We're just talking about the weldability in material in general. And when you talk to people that aren't, mechanical engineers or civil engineers, and you ask, well, what material is it? And they don't, I don't know. It's this. And it's like, steel? Well, what kind of steel? Narrow it down for me so I can, help you. How about you help me help you kind of thing? And, education on educating them, and then also educating your welders that, hey, this stuff is very tricky and we need to follow some rules while welding it. So if you're looking at post-weld heat treatment, if you look in ASME B31.1, B31.3, or ASME Section 1, there is like pages upon pages of post-weld heat treatment for the different P numbers. And it gives you a general outline of what needs to be done, and then there's about 3/4 of a page of exceptions or little caveats that you need to look at for thicknesses and whatever. So, with that being said, here is my version of post-weld heat treatment for ferrous materials, carbon steels, and whatnot. These are the 3 biggies. Steel composition and processing. What is the chemistry? You know, you got to look at the chemistry of what's being post-weld heat treated and how it was processed. Quenched and tempered or something. Are you going to mess it up if you post-weld heat treat it? Or if you post-weld heat treat it too long, are you going to turn it into absolute mush? You know, you're going to take a material that was supposed to have a certain hardness and you're going to cook that hardness out of it, basically anneal it. You know, you got to look at the weld metal and the HAZ properties you're looking for. You know, these need to be taken into account when you're looking at post-weld heat treatment. And the thickness of the material also comes into play. Because if you put something in the oven that's 10 inches thick and you just cook the outside, you know, you post-weld heat treat the outside and you don't get the inside, well, then you kind of defeated the purpose, right? So these are the things, to me, I'm trying to boil down pages upon pages of post-weld heat treatment into 3 lines. And to me, it is steel composition and the, you know, what processes have been done to get it to those mechanical and physical properties that you're looking for, the processing, the weld metal and HAZ properties, and the thickness of the material. Steel composition and processing. Weldable structural steels for use at ambient or moderately elevated temperatures fall into 4 categories. Key word here, structural steels. Carbon and carbon manganese steels, high strength low alloy steels, normalized and tempered high tensile steels, and quenched and tempered high tensile steels. And each one of these categories has its own nuances involved in being able to weld it and have a weld come out, you know, that meets the criteria for the weld joint and matches the, you know, the base material and, you know, the tensils and the hardnesses, and make sure you don't have a messed up heat affected zone. So, yeah, these are pretty much the 4 categories, and each one of these is a different animal. I'm not going to go into each one in detail, but we're kind of covering some of them. Main alloying additions in steel. So steel is iron, and you throw in some carbon. So carbon is a potent solid solution strengthening element in iron. It's the biggie. Carbon increases tensile strength but reduces ductility. So you make a really sharp sword that's got a really high tensile strength, but you're going to be able to shatter it too, to some degree. High carbon content promotes formation of hard, brittle microstructures on cooling from above the phase transformation temperature. This gets back to Metallurgy 101 when we're talking about steel going through a allotropic phase transformation when it goes from body-centered cubic to face-centered cubic, you know, back to body-centered cubic, and then into a liquid, or, you know, and then cooling it all down really fast, and you end up with martensite, which is body-centered tetragonal. But anyways, high carbon, the more carbon you put in there, and then you heat the material up above the phase transformation temperature, and then you cool it really quickly, all that carbon that was dissolved in solution doesn't have anywhere to go. So that's why we throw in manganese sometimes to increase strength without reducing ductility. It improves notch toughness and reduces hot cracking. So a lot of times you'll have, you'll throw manganese in a steel like it says here to get, it increases the strength, but you're not losing the ductility. So it's not a really hard, high tensile strength piece of glass, so to say. The manganese helps keep the ductility in a range that's something you can work with. It makes it a useful tool. So along with the things that we want in steels like carbon and manganese, there's also a lot of impurities that get left in there. If you look back on how they made steels, in the 1800s, a lot of impurities before they figured out how to clean the material up. So sulfur, phosphorus, oxygen, and nitrogen are the biggies. Phosphorus decreases toughness. Phosphorus and sulfur form low melting compounds that promote weld and HAZ solidification cracking. Oxygen and nitrogen form dispersions of oxides and nitrides that strengthen the metal and reduce its ductility. So these are all things that when they're making steels, you don't want a lot of sulfur, phosphorus, oxygen, or nitrogen in your weld pool or in your weld metal in general. And I've read some things where they think part of the reason like the Titanic might have sunk is they had really dirty steel. Some of the rivets might have been made out of really low grade steel, and they needed so much steel to make that ship that it was that they could have been getting a lot of material that was substandard material. But I don't know if that's here nor there, but it's something to think about. So these are things you do not want in your steel. So generally most specifications have a limit on how much sulfur and phosphorus you can have in your material. So something to keep in mind as you're looking at welding certain materials and realizing, hey, these are the bad actors in there and they can mess things up. Steel developments. In recent decades, new steels have been developed which offer a combination of strength, ductility, and toughness. Steps in achieving these benefits include some or all of lower carbon contents, lower impurity contents, full deoxidization and fine grain practice, small alloying additions of nickel, chrome, moly, copper, vanadium, titanium, zirconium, and aluminum, controlled rolling temperatures, and normalizing and quenching treatments. And once again, this is just a one slide look at steels over the last 50 years, but these are some of the things they're doing that, to make cleaner, better steels that are better than something that was made, in the 20s or 30s. So, microalloying with the nickels, the chromes, things like that. And, keeping the impurities low and low carbon contents. So there's a lot of different things that they've done. And, that's kind of outside the scope of what we're looking at here. But some of these materials are readily weldable and easily weldable, and some are a little more difficult. And you might have to do your research and really develop a weld procedure that fits that material. Traditional carbon manganese structural steels relied on solid solution strengthening from carbon and manganese to reach a given strength. Higher strength meant higher contents of these elements, generally carbon above 0.35%. Combined with high impurity contents, it led to poor weldability. So if you're getting your carbon content up there and then you have things like, phosphorus and sulfur in there and other impurities, it's going to lead to poor weldability. Here's some steel specifications. You've got the A36 and the A105 and the A106, which are generally P1 materials in AWS or ASME, ASME Section 9 for weldability. And then I think most of those are group 1s for AWS D1.1. Then you get to 514 and 515. A514 is a high yield strength quenched and tempered alloy steel plate suitable for welding. And I'm thinking that's some of the material they make haul truck frames out of. I mean, it's a material that can take a beating. 15 is A515 is pressure vessel plates, carbon steel for intermediate and high temperature service. 516 is carbon steel, moderate low pressure, lower temperature service. And then A706 is structural steel for bridges. So these are just some random ASTM specifications that, you know, seem to come up more often than not, and you might run into these materials. Here are a couple organizations that have steel specifications. The American Society for Mechanical Engineers, ASME and ASTM material specifications. A lot of times they're dual listed. ASME material specifications are used for pressure vessels and piping. Well, and in can-do reactors. All right. Considering I snagged their PowerPoint. The American Petroleum Institute, they've got all kinds of materials listed for different kinds of pipes that fall outside the range of something that ASTM or ASME would use. So these are some steels you might want to look at some point if you're building something and you need pipe. High strength, low alloy steels. Steels incorporating small alloy additions are known as high strength, low alloy steels or microalloyed steels. High strength, low alloy steels up to about 70 KSI ultimate tensile strength with carbon content up to 0.2% and made with deoxidized fine-grained practice are readily weldable. So there's a whole list of high-strength, low-alloy steels that are readily weldable. Just need to follow the directions and make sure your workforce is on board with what you're doing, and generally shouldn't be too much of a problem to weld this stuff. Quench and temper steels. Steels that rely on quench and temper heat treatment to obtain a very high strength are more susceptible to welding problems and require specific metallurgical expertise. For example, ASTM A514. I looked up on some manufacturers' data sheets on, welding ASTM A514. And these are the listed shielded metal arc welding electrodes that are suggested. So we're not just talking about a 90-15 or a 90-16 or a 90-18. We're talking 110-15, 110-16, and 110-18. So when I was telling you back when, I see to me it's a red flag, 80 and 90, I really start to go into overdrive when I see the tensile strength of my filler metal needs to be 110. So it just means it's weldable, but you just got to be careful and follow the rules. So it's not something to dabble in lightly, but it can be done. Do some research, dig through the American Welding Society, welding handbooks, and do a Google search on welding this stuff, and you can put together a pretty solid welding procedure in no time. But just realize you're playing with fire here. You're dealing with a material that, you should handle with some care and some level of expertise. Properties of the HAZ. The response of the parent metal and reheated weld metal in multi-pass welds to the weld thermal cycle determines the properties of the weld heat affected zone. The main factors are steel composition and processing, peak temperatures, and cooling rates. The yield and ultimate strength of the HAZ are usually higher than the parent metal, so the main properties of interest are hardness and toughness. So this is just telling us that you got to watch that, because with a weld, there's a thermal cycle, right? You're heating the material up, you're cooling it down. You're heating it up, you're cooling it down. Let's say your guys go away for lunch. It cools all the way back down to room temperature. You preheat it, and then you weld like hell for a while, a few hours, and you heat that piece of metal up, and it cools down, and it heats up, and, there's a lot of stresses that are introduced into that piece of material. So that's why we worry. And it's not just the weld we're worrying about. We're worrying about the heat affected zone. How wide's that heat affected zone? Are we watching our heat input into that material? What do we got really going on there? So, and we're talking about the yield and ultimate tensile strength are usually going to be higher than the parent material in this. So we really need to watch out and make sure we don't have a heat affected zone that's going to be harder, softer, or outside the boundaries of what our materials should look like. So we really need to keep an eye on the HAZ. A lot of times when you'll do a weld procedure qualification, you'll have, the HAZ, they'll do a bunch of tests on the HAZ and, hardnesses and whatnot so that you can, have a good idea of what your weld's going to look like as far as hardness and ultimate tensile strength, as well as your HAZ, and then see how big your HAZ is going to be. HAZ hardness. Hardness is a measure of tensile strength and degree of embrittlement. In carbon manganese steels, HAZ hardness exceeding 350 HV, hardness victors, is considered excessive. HAZ hardness is determined by alloy content and cooling rate in the transformation temperature range. Fracture toughness of the HAZ. Factors affecting toughness are the weld thermal cycle, grain coarsening temperature of the steel, transformation characteristics, and alloy or impurity content. Gets back to us talking about, what's in there, phosphorus, sulfur, what kind of impurities are in there. What was the thermal cycle of the welds? Has it been heated up, cooled down, let to sit, started up again, sat in the rain? What happened to this piece of material? And these all affect the fracture toughness of a material. If the fracture toughness of the parent steel is low, the toughness of the HAZ is usually low, and conversely, fine grain practice and microalloying benefit the HAZ as well as the original material. Low heat input welding procedures give a finer HAZ grain structure and better toughness in low carbon equivalent steels. However, in steels with a high carbon equivalent content, HAZ hardness considerations set a minimum heat input. It is sometimes difficult to get adequate toughness in high carbon equivalent steels. That last one is, we used to go round and round trying to qualify weld procedures for use in oil type situations. And they'd want a really high tensile strength and they'd want a really good toughness. And it was really difficult sometimes to hit that sweet spot because you get too high of a tensile strength and your toughness is going to go to hell in a handbasket. So it's trying to hit that metallurgical sweet spot and then not, depending on what heat treatment you're doing and what filler materials you're using, it can be a real balancing act trying to get everything just fine tuned. So something to think about when you're welding this, and looking for fracture toughness and a high tensile strength. Weld metal tensile strength. The factors that govern the tensile strength of the weld metal are the carbon content. Carbon and manganese increase strength. I don't know how many times I've said that or will say that in this presentation. Ferrite grain size. Tensile strength increases as the ferrite grain size is reduced. Summary of the weldability of steels. Kind of trying to wrap this up before it turns into a 6-hour Gary Pace rant on how the universe functions. But anyways, my universe, the ideas that I've gleaned from others on the factors affecting weldability are steel composition and processing. What's in that steel and how was it processed? Quench and tempered or something, whatever, annealed, who knows? What HAZ, weld metal, and properties are we looking for? Welding variables, how travel speed, heat input, all these kind of things, those play a huge choice or a huge role in the weldability of steels. And then what do we need to do to the material before and after we're done welding it? Do we need to preheat it, post-weld heat treat it? Thickness is another one that really comes into play in my mind. If we're welding 6-inch thick pieces of material, that's a hell of a lot different than welding 1/2-inch thick material. So that's another one comes into play. And then welding processes, what welding process are we going to use? There's a number of these, but basically that's what we covered. I also touched base on a little bit of, how ASME and ASME or AWS and the American Society of Mechanical Engineers, view weldability of steels and kind of break it out. And I also threw in there my red flags. Like, if you see this, you need to stop and evaluate your situation before you go forward. So anyways, I hope we touched base on some things and you got some information out of this. Any questions on weldability of steels, questions, comments, something you'd like to see in the future, give me a shout. There's my email address or my website. Anyways, everybody take care. GP out.